Okay, so hello and welcome back. So the rest of the exercise is 1.4, question number 3. We have considered the binary operation minimum. Now, question number 3 is consider the binary operation minimum and the set 1, 2, 3, 4, 5. And the set 1, 2, 3, 4, and 5. Defined by A minimum B is the same thing as min of A and B. Min of A comma B. Write the operation table of the operation minimum. You want to write the operation table. The operation table of the operation minimum. Okay, so basically this operation is a binary operation on this set. If we call this set A, for example, let's write, so as the solution, let us denote A equal to 1, 2, 3, 4, and 5. Let's denote the set as set A. So we have this operation on this set. We have the operation star on A. That is, we have the star as a binary operation on A, defined as basically star of or A star B, defined as A star B is equal to A, this is minimum, of course, A minimum B, which is equal to min of A comma B, right? Now what we need to do, we want to write the operation table of the operation minimum, which means that basically any okay, so now for the solution, basically the table is going to have basically 5 rows and 5 columns, and so the 5 rows will be something like this, meaning that you will have a table like this. And of course, what I mean by 5 rows is, the way that I understand it is basically in the text there is a mention of 5 rows, and I basically normally you get 6 rows over here, but I think what they mean is, by the 5 rows they mean basically 1, 2, 3, 4, and 5, meaning that you get 1, 2, 3, 4, and 5 here, and 1, 2, 3, 4, and 5 here, 1, 2, 3, 4, and 5 here, and then you have basically 5 columns here, and you have 5 rows here. That's the way that I understand it. Otherwise, what is mentioned in the text, that's the only way that makes sense. which is not that important for now. What is important is that basically here you have the operation, the binary operation. Here you have the binary operation minimum, and so this is minimum and this is maximum. Right? This is the two functions. So and basically A star B, you can take this all as A and all of these as B. So then A star B is A minimum B, which is the same thing as minimum of A and A comma B, which is 1 and 1. The minimum would be 1, 1 and 2, 1, 1 and 3, 1, 1 and 4, 1, 1 and 5, 1, 2 and 1 would be 1, 2 and 2 would be 2, 2, 2 and 2, 1, 3 and 2 is basically 2, 3 and 3 would be 3, 3 and 4 would be 3, 3 and 5 would be 3, 4 and 1 would be 1, 4 and 2 would be 2, 4 and 3 would be 3, 4 and 4 would be 4, 4 and 5 would be 5, and 5 and 1 would be 1, 5 and 2 would be 2, 5 and 3 would be 3, 5 and 4 would be 4, and 5 and 5 would be 5. I suppose that is the solution here. So so basically, if you care about this, if you care about order and basically a couple of well formulated logical sentences as well, you can say that basically apart from this table, you can of course say that the binary operation minimum on the set 1, 2, 3, 4 and 5, 1, 2, 3, 4 and 5 is defined as basically A minimum B, which is the same thing as minimum of A comma B for all A and B, for all A comma B belonging to this set 1, 2, 3, 4 and 5. That's the operation table for the given operation. Then you can say that thus the operation table for the given operation minimum can be given as above, and as this table basically. And then the table is basically this table that we have basically arranged over here. We have 1, 1, 1, 1 and 1, 2, 2, 2 and 1, 2, 3, 3, 3 and 1, 2, 3, 4, 4 and 1, 2, 3, 4, 5. Okay. Now you might think that this is superfluous or unnecessary to write down all of these things, but sometimes it's important because this way you will get used to writing things down, and when you write things down, most of the time you will basically come across points or come across things in your thinking that when you look at them on a piece of paper, then you will realize that, meaning that when you take the time to write them down and think about it, then you will realize that what you were thinking was actually logically not right. And so then you get over your own logical mistakes, and if you don't do this, you might actually keep all of those mistakes for forever or for a long time. So basically what I have, and I'm saying this based on the fact that, for example, when you learn, for example, when you're learning physics, for example, a physics book is usually, well, if the book is, it doesn't have any problems, or if the text is not confused, then most of the time you can read the text. If you read it carefully, you will have no problem and you will understand it. But most of the time, the text that you read is either confused itself in the first place, or the way that you make sense of the text is not the way that you're supposed to make sense of the text, meaning that they have written some words or some sentences or some statements, and they have, well, most of the time people have to use words and sentences loosely. I mean, when it comes to the English language, things can be defined in multiple ways. So when what they wrote, as basically what they meant by what they wrote, was a completely different thing, and now your understanding of what you read from the text is a completely different thing, and then you will get into problems of misunderstanding, logical problems, and that sort of thing. And usually when you write your things down this way, you will give yourself a chance, or you will be given a chance to actually look at what's going on in your thoughts. And then once you do that, you might actually see that you haven't understood something not right or not correctly, or you have understood something in a way that you weren't supposed to understand it, or so on and so on and so on. And there is many different types of possibilities, of course. So it's actually a good idea to write things down and be basically neat and orderly in your writing, in your thinking. It's actually almost always beneficial. Okay, so I don't want to give you a philosophy lesson. Now, question number 4 is, consider a binary operation. Okay, so basically the next question that we have is question number 4, that says, consider a binary operation star. Consider a binary operation star on the set 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5, given by the following multiplication table. Given by the following multiplication table. They have called it a multiplication table, meaning that basically the operation is most probably multiplication, but let's see. And the table is, now you want to compute, number 1, you want to compute 2 star 3, 2 star 3 star 4, and 2 star 3 star 4. and is star commutative? Is star, actually I have to write star as star, so is star commutative? And number 3, compute 2 star 3 star 4 star 5. Compute 2 star 3 star 4 star 5. And use the following table. Of course, the table is something like this, or exactly this table, which you have all of these rows. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 6. And you have basically another 5 columns here. 2, 3, 4, and 5. And so you have you have the operation star here, and you have 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. And then you have 1, 1, 1, 1, 1. You have here 1, 1, 1, 1, 1. 1, 2, 1, 2, 1. 1, 2, 1, 2, 1. And then you have 1, 1, 3, 1, 1. 1, 1, 3, 1, 1. And then you have 1, 2, 1, 4, 1. 1, 2, 1, 4, 1. And then you have 1, 1, basically 4 ones and a 5. So that is the table that you have. And now let's see how we can use this table. Okay, so that is the table. Now, so all that I know is that, for example, 1 star 1 is equal to 1, 1 star 2 is equal to 1, 1 star 3 is equal to 1, 1 star 4 is equal to 1, 1 star 5 is equal to 1, and so on and so forth. For example, 2 star 4 is equal to 2, and so on and so forth. So to solve the problem, what you can do is that to calculate, for example, 2 star 3 star 4, you can write it as 2 star 3 is equal to 1. So that is 1 star 4, which is equal to 1. And 2 star 3 star 4, 2 star 3 star 4 is the same thing as 2 star. Now 3 star 4 is equal to 1. Now 2 star 1 is equal to 1. Right? So that is that. Now you want to find out whether star is commutative. If star is supposed to be commutative, basically this was part 1. So in order for star to be commutative, then basically the condition is that A star B has to be equal to B star A for all A and B belonging to the set that we are talking about. For example, let's call it the set X or whatever the set might be. So now I think the only way that we can find out here is that because we have no rule here, we have only a table, and so the only way that we can find out is that we have to you see we can actually check on the table, meaning that, for example, 1 star 1 is equal to 1, and then again 1 star 1 has to be equal to 1, which is the case. So for example, 1 star 2 is 1, 2 star 2 is 1, 1 star 3 is equal to 1, 3 star 1 is equal to 1, 1 star 4 is equal to 1, 4 star 1 is equal to 1, 1 star 5 is equal to 1, 5 star 1 is equal to 1. So we have no problem with basically with the first range of numbers, or whatever you want to call it. Then you can start from 2, and then you have to go for example, 2 star 1, and then again relative to this you have to check also 1 star 2, and they have to be equal, and then you have to move to, for example, 2 star 2, and then you have to move to 2 star 3, and all the way up to 2 star 5. 2 star 5, and then this has to be equal to, for example, 2 star 2. This has to be equal to 3 star 2. This has to be equal to, and this has to be equal to basically 5 star 2. 5 star 2. And then you need to do the same thing for example, starting from 3. Then, for example, 3 star 1, you need to calculate that, and then check 1 star 3. They have to be equal. For example, 3 star 2, you check that, and then compare that with 2 star 3. And then you need to go all the way up to 3 star 5, and then compare that with 5 star 3. And then you need to just keep going, meaning that 4 star 1, 4 star 2, 4 star 3, and so on and so forth. And then you need to end with 5 star 5, and compare it with 5 star 5. That way you can make sure that the star is commutative. So we already did basically 1. We already started with 1, and we had no problem there. So the next round will be 2 star 1, for example, which is equal to 1. 2 star 1 is equal to 1. So 1 star 2 is equal to 1. 2 star 2 is equal to 2. 2 star 2 is equal to 2. 2 star 3 is equal to 1. 3 star 2 is equal to 1. 2 star 4 is equal to 2. 4 star 2 is equal to 2. 2 star 5 is equal to 1. 5 star 2 is equal to 1. So we have no problem with 2. If you start with 3, then 3 star 1 is equal to 1. 1 star 3 is equal to 1. 3 star 2 is equal to 1. 3 star, let me go a little bit more slowly. 3 star 1 is equal to 1. 1 star 3 is equal to 1. 3 star 2 is equal to 1. 2 star 3 is equal to 1. 3 star 3 is equal to 3. And well, then 3 star 3 is equal to 3 again. And 3 star 4 is equal to 1. 4 star 3 is equal to 1. 3 star 5 is equal to 1. 5 star 3 is equal to 1. So we have no problem with 3. Now starting with 4, 4 star 1 is equal to 1. 1 star 4 is equal to 1. 4 star 2 is equal to 2. 2 star 4 is equal to 2. 4 star 3 is equal to 1. 3 star 4 is equal to 1. 4 star 4 is equal to 4, whatever that might be, it doesn't really matter. 4 star 5 is equal to 1. 5 star 4 is equal to 1. So we have no problem with 4. And then 5 star 1 is equal to 1. 1 star 5 is equal to 1. 5 star 2 is equal to 1. 2 star 5 is equal to 1. 5 star 3 is equal to 1. 3 star 5 is equal to 1. 5 star 4 is equal to 1, 4 star 5 is equal to 1, 5 star 5 is equal to 5. So yes, basically you can say that therefore star is commutative. Is commutative. And this the third part of this question. So let me erase all of this so that we have some space over here. So we can say that yes, star is commutative. By checking the table, right? Now part 3 of this question. Part 3 of this question, we have compute 2 star 3. You have compute 2 star 3 star 4 star 5. Star 4 star 5. Now 2 star 3 is equal to 1. Star 4 star 5 is equal to 1. And 1 star 1 is equal to 1. So that's basically all of the different parts of this question, right? So now let me take a look at the solution here. So answer is 2 star 3 star 4 is equal to 1, 2 star 3 star 4 is equal to 1. For every A, comma B belonging to this, we have A star, therefore the operation is commutative. That's exactly the kind of reasoning that I used. And that is equal to 1. Okay. So now the next question is question number 5. Okay, so now let's do question number 5, which is let star prime be the binary operation on set 1, 2, 3, 4, 5. So question number 5 is let star prime be the binary operation on the set 1, 2, 3, 4, and 5, defined by A star prime B is equal to HCF, the highest common factor of A and B. So the HCF of A and the highest common factor, I'll tell you what that means. It's the operation star prime is the operation star prime the same as the operation star, defined in exercise 4 above, and you want to, of course, you need to justify your answers. So star prime is the binary operation on the set 1, 2, 3, 4, 5, defined by this rule, and we want to know if it is the same is if star prime is the same as the operation star defined in exercise 4 above, meaning that the images are going to be the same. So of course you can, I think the only way to do it is to draw a table for this operation and see if the outputs are the same. If the outputs are the same, then you can conclude that the operations are the same, otherwise not. But before I do that, let me take a look at the solution to see if my logic is right. Otherwise, we would be spending unnecessary time on something which is logically not right. Okay, that seems that that's the same thing. Okay. So now if I do a table for this, I have basically all of these rows and columns here. So I have basically 1, 2, 3, 4, and 5, and then I need another column as well. And then I have basically 1, 2, 3, 4, and 5. So 1, 2, 3, 4, 5, and 6. So now what we have here is this table, and here I have star prime. Here I have star prime, and these are the sets that I have: 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. And well, basically A star prime B is the same thing as the HCF of A and B. That is the rule that we have here. So what that means is that the HCF means the highest common factor. HCF means the highest common factor. The highest common factor. And what that means is that, for example, suppose that you have the numbers, for example, 1 and 1. So 1, you can write it as 1 times 1. And 1 again over here, you can write it again as 1 times 1. So the common factors of these two numbers, when you prime factorize them, of course 1 is not a prime number, but I suppose it doesn't really, probably, I'm saying probably doesn't matter here, because this operation is anyway defined on these numbers, so it must be in some way, shape, or form okay to assume that, I mean, at the end of the day, you're able to perform this operation on these numbers, so you have no problem with that. So now if I assume that the factors of 1 are 1 and 1, and the factors of 1 are again 1 and 1, and these are the two numbers, meaning that if I want to calculate 1 star prime 1, so then that basically means that this is equal to the HCF of 1 and 1, right? So now to calculate the HCF of 1 and 1, I need to factorize 1, and again I need to factorize 1, and all of the common factors I have to specify them, meaning that the common factors that I have here is 1 is common between the two, and again 1 is common between the two. And then since 1 is common between the two, and again 1 is common between the two, when you multiply them together, you'll get a 1. So that means that this is equal to 1. So the highest common factors of these two numbers becomes 1. And that is equal to 1, for example. Now basically, for example, the highest common factor of 1 and 2 would be 1 is the same thing as 1 times 1, and 2 is the same thing as 1 times 2. So as you can see, 1 is common between the two numbers. But then 1 and 2 are not common, so you can forget about them. And so the HCF of, for example, 1 and 2 is equal to 1. Just a simple 1. Or 1 and 3, again, the same story. 1 and 4 is 1, 1 and 5 is 1. And the reason for this is that, for example, the reason for that is that, for example, 3, you can write it as 3, you can write it as 1 times 3. So then you would have this factor common with 1. But 4, you can write it as 2 times 2, or you can write it as 1 times 4, meaning that the factors of 4 are actually 1 and 2 and 4. The factors of 4 are actually 1. The factors of 4 are actually 1 and 2 and 4. Or the factors of 5 are 1 and 5, because 5 is a prime number, right? So you don't get any, you get only the number itself and 1. And again, when it comes to 2 and 1, you will get a 1 over here. When you get to 2 and 2, 2 is the same thing as 1 times 2, and again 2, and then again 2 is the same thing as 1 times 2, so you have a 1 in common, 2 in common. 1 times 2 is equal to 2. The highest common factor of 2 and 3 is again 1, because you have 1 times 2, 1 times 3, 1 is common. 2 and 4 is basically only 2, I suppose, because 2 is the same thing as 1 times 2, and 4 is the same thing as 1 times 4, and also 4 is the same thing as 2 times 2. So that means that 4, the factors of 4 are basically 1, 2, and 4. 1, 2, and 4. So if I take 1 and 2 and then multiply them together, I get a 2 over here. And 2 and 5, then again you will get to 1, because that's the highest common factor of 2 and 5, because they are mainly basically prime numbers. 3 and 1 is 1, both, of course 1 is not a prime number, but 3 and 1 would be 1, 3 and 2 would be 1, 3 and 3 would be 3. 3 and 4 would be 1, 3 and 5 would be 1. And 4 and 1 would be 1, 4 and 2 would be 2, 4 and 3 would be 1, 4 and 4 would be 4, and 4 and 5 would be 1. And 5 and 1 would be 1, 5 and 2 would be 1, 5 and 3 would be 1, 5 and 4 would be 1, 5 and 5 would be 5. So if we take a look at the table up here that we had, we make a screenshot here. So this is the table of star that we had related to the previous question. And if you compare these two tables, you'll get, this is star prime, and you'll get 1, 1, 1, 1 old ones here, 1, 2, 1, 2, 1, and 1, 1, 3, 1, 1, 1, 2, 1, 4, 1, and 1, 1, 1, 1, 5. So the same, you get exactly the same outputs or images for these two, basically for the two different cases, which means that we observe that the operation tables for the operation star and star prime are the same. Thus, the operation star prime is the same as operation star. So we observe that that the operation tables, that the operation tables of star and star prime are the same, thus the operation star prime is the same as the operation star. It's the same as the operation star. That's basically question number 5. Okay, so let's do another question here as well. So question number 6 is let star be the binary operation on n. Let star be the binary operation on n. Let star be the binary operation on n given by a star b is equal to LCM of a and b. LCM of a and b. Find number 1, 5 star 7, 20 star 16, 20 star 16. Number 2 is star commutative. Number 3 is star associative. And find the identity of star in n. Number 4, find the identity of star in n. And number 5, which elements of n are invertible for the operation star. So we have quite a couple of questions here, so we will go through them one by one. Okay, so basically question number 6 is basically let star be the binary operation on n given by a star b is equal to LCM of a and b. Now I'll tell you what basically LCM is. Most probably you know it already. So you want to find 5 star 7, 20 star 16, and you want to know whether basically whether star is commutative or is it associative, and you want to find the identity of star in n, and also you want to know which elements of n are invertible for the operation star. So this is a good question because it uses almost everything that all the concepts that we have learned in this section of this chapter. So, and but we will start with the concept of LCM. So basically the LCM of two numbers is basically is the least common multiple of those two numbers. So LCM means the least common multiple. The least common multiple. And what that means is that basically for example, if you want to add two fractions, for example 1/20 and 1/16, right? You want to add these two numbers. So in order, I need to basically make I cannot add 1/20 to 1/16 if I had, for example, 1/2 and, for example, 2/2. Then of course I could add them together because the denominator in both of these fractions are the same. So I can write 1/2 plus 2/2, and I can write the denominator as 2 and write this as 1 plus 2, which is equal to 3/2. So here I have no problem. And here, as you can see, that the denominators were basically the same. So I took the denominator, I put it here, and then add the numbers in the numerator together, and then that becomes the answer here, and you have no problem here. But then the problem here, then you will get a problem here, and that is basically if you have 1/20 and 1/16, the denominators are not the same, meaning that if I were to add these together, I wouldn't know if I were to use 20, if I were to use 20, or if I were to use 16. And well, of course I could use neither of them because they are not the same. So I need to find a way in order to make these denominators the same. So what I can do, for example, in this case, I can take these fractions, take one of them, and basically, for example, I can take this fraction, divide both the numerator and denominator by 5, right? So for example, 1/20, I can divide the numerator and denominator by 5, and my goal here is to get the denominator to 4 and then multiply it by 4, because 4 times 4 is equal to 16. So how do I get to 4 from 20? I have to divide by 5. So since I have to divide by 5, I write 1 divided by 5 divided 20 divided by 5. That gives me 1/5 divided by 20/5 is equal to 4, right? And now if I multiply 4 by 4, I will get a 16, and then that would be the same denominator as the denominator of this fraction here. So I write 1/5 times a 4, and 4 times a 4, and that gives me 4/5 divided by 16, right? So now I know that 1/20 is the same thing as 4/5 divided by 16, and so now I can write this as 4/5 divided by 16 plus a 16 plus a 1/16, and that is the same thing as, now I can write basically the common denominator as 16 here, and then add these two together, meaning that 4/5 plus 1, and 1, you know that 1 is the same thing as, for example, you can write it as 5/5, right? So I can write this as 4/5 plus 5/5 divided by 16, and so 4/5 plus 5/5 is equal to 9/5, divided by 16. Now this is the same thing as 9/5 times the reciprocal of the denominator. This is 16 divided by 1. So the reciprocal of that becomes 1/16. So now 5 times 16 is equal to what? Is equal to 50 and 90. That's 9 divided by 90, which is 1 divided by 10, which is equal to 1/10, right? So you see that I have to do all of this operation in order to add these two fractions together, right? And I did all of this operation so as to get one of the fractions to have the same denominator as basically one of the other fractions, and then so that I could add them together, right? Now there is a technique that we can use in order to basically there is a technique in order to get over this problem. So one thing that you can do is that you can write 1/20 plus 1/16, and I want basically, well, of course I know that these two are not the same denominators, but I can just simply multiply them together. That would be 320, and 320 is divisible by both of these numbers because it's a multiple of 16 and also a multiple of 20. So if I divide 320 by 20, I'll get a 16, and 16 times 1 is equal to 16. And so 16 divided by 320 is actually 1 divided by 20, right? If you tried 16 divided by 320, divide by 16, you'll get 1, divide by 16, you'll get 20, that's 1/20. It's the same thing that we started with here. And 320 divided by 16 is equal to 20, 20 times 1 is equal to 20, and that's the same thing as 20 plus 16 is equal to 36 divided by 320. And then you can of course simplify this fraction, meaning that you can divide by, I don't know, you can divide by many things. For example, 36 divided by 2 is equal to 18, 320 divided by 2 is equal to 160, divide by 9, divide by 280, and divide by there must be something wrong here, I suppose. Or maybe I have made a mistake here, probably somewhere over here. Let me see what is, use my calculator here to see what is 1/20 plus 1/16. 1/20 plus 1/16 is the same thing as 9/80. That is correct. That is correct, but there must be something wrong here. 50, yeah, that's 80 actually. The problem is here. The problem is here. So here, when you write, I made a mistake in calculation here. So 9 times 1 is equal to 9, and 5 times 16 is equal to 80. 9/80. So this is the same thing as 9/80, the same number, right? So as you can see, in order to get over that problem, what I did was that I multiplied both of these numbers together, and I got this number. Then I had to divide this number by both of these numbers, and then whatever I got, I multiplied by the numerator and wrote it over here. Again, the same thing, wrote it over here, added these two together, and then we got the answer over here. And that was how we did the calculation. Now this has a problem, which is, suppose that you're trying to find the for example, 25 divided by 25,362 plus, for example, 36 divided by 36,898. So now if I were to use the same method that I used here, what I need to do is to basically multiply these two numbers together. This number I have to multiply it by this number, and will give me some very large number, and it would not be easy to deal with that sort of number. So now so now my goal here is to basically to find some number a for the common denominator here. I want to find some number a which is divisible by both 25,362 and also 36,898, and moreover the number must be the smallest such number that can be found, that the smallest such number that can be found, right? So of course I know that the number which is divisible by both 25,362 and also 36,898, that number is basically the product of these two numbers. That I already know. But then I also know that if I multiply these two numbers together, I'll get some very large number. Now I want to know if it's possible to find some number which is divisible by both of these numbers, and possibly not be as large as the product of both of those numbers, right? And so now, in order to solve that sort of problem, you need to use the concept of, you need to understand the concept of LCM, which is the least common multiple. Now, the least common multiple is basically very simply, for example, when you want to calculate the LCM, suppose that you want to calculate solving the same problem 1/20 plus 1/16. 1/20 plus 1/16. So now, this time, basically the previous time we multiplied these two numbers together and we got 320 and some numbers over here, and we did the calculation. So this was basically the product of the two numbers. Now let's calculate the LCM of 20 and 16. Let's calculate the LCM of 20 and 16 and see what that is. So the LCM of 20 and 16, to calculate that, what you need to do is basically you need to factorize 20, or prime factorize it. Meaning that, for example, 20 is 2 times 10, and that is 2 times 5. Which means that 20 is the same thing as 2 times 2 times 5. And also a 16 is the same thing as basically 2 times 8 and 2 times 4 and 2 times 2, which is 4 factors of 2 multiplied together. So that's 2 raised to 2 times 2 times 2 times 2. So what that means is that now I'm looking for a number. I am looking for a number which is basically since the number that I'm looking for it's supposed to be divisible by 20, meaning that it needs to have at least a 20 in it. And it also needs to be divisible by 16, which means that it needs to have at least one factor of 16 in it. So one factor of 16 means 4 2's. One factor of 20 means these factors, these prime factors here, which means that the LCM of 20 and 16 is simply the same thing as all of these factors, which is, since I need to have at least one 16 in that number, so I write 2 times 2 times 2 times 2. That takes care of my 16. So my 16 is now taken care of. And also I need a 20 in my number. Now you see that the 20 needs 2 factors of 2. But then the 2 factors of 2, I already have them over here. I have 4 factors of 2. But at least 2 I have already in my number. So I don't need to worry about the 2 factors of 2. So the only thing that I need for a 20 is therefore a 5. So I just add a 5 over here. And as you can see, now if I take these numbers together, these factors together, that gives me a 16. And if I take this number, and this factor, these 3 factors together, that gives me a 20. So this number, whatever that is has a 16 in it. It also has a 20 in it. That means that it's divisible by 16 and also divisible by 20. And also it is the smallest such number that you can find, which is divisible by 20 and also divisible by a 16, right? So now this number is the same thing as basically 16 times 5, which is equal to 80, right? That is equal to 80 because you have 10 times 8 is equal to 80, right? So this is equal to 80. Now, so what that means is that I can simply write this fraction, this calculation as 1 divided by 20 plus 1 divided by 16 is the same thing as, and I write the denominator as 80. 80 divided by 20 is 4, and 80 divided by 16 is equal to 5, I suppose. Right? 5, yes, 5, because 5 times 16 is equal to 50 and 30, 80. So that's 9 divided by 80, which is basically the number that we had before, right? So that is the concept of the LCM and how elegant and useful it can be in many different types of situations. So basically an LCM is an LCM of 2 or more numbers is a number which is divisible by all of those numbers, and also the smallest such number that you can find that is divisible by all of those numbers. That's basically what an LCM is. Now what we have here is basically then the question that we wanted to answer was basically we wanted to know we wanted first to find the LCM of these numbers. So now that we understand what an LCM is, we will continue the rest of this discussion in the next video. I'll see you in the next video. Thank you.